Okay, I want to continue on with a few of these short sessions on introducing topics from our class. So I want to talk about the gradient vector today. So last time we talked about limits, and we talked about the partial derivative with respect to x and y of a two-variable function f. And today I want to start talking about this other topic known as a gradient vector. So I'm going to start with letting z equal to f of xy be a differentiable function. So f is a function of two variables, x and y, and I'm thinking of z as being the output, the dependent variable in this situation. And last time we've seen how to take derivatives of f in both the x and y directions. And our notation for that was the partial derivative of f with respect to x and the partial derivative of f with respect to y. And you can think of these in these two partial derivatives as if I have these coordinate axes x and y in the domain of f, then the partial derivative of f with respect to x is the change in f as I move directly in the I direction, where I is the standard unit vector, 1, 0. And likewise, the derivative with respect to y is that measures the change in f as I move a little bit in the y direction, keeping x constant. And there's a natural question that arises is, how do we take the derivative of f in other unit directions u? So how do I take the derivative of f with respect to other vectors u where I'm going to require u is always a unit vector? And the answer to this comes out of this new idea, this new concept known as the gradient vector. And here's the definition of the gradient vector. We define the gradient of a function f of xy, and it's denoted by this upside down triangle with a vector symbol over the top of it. So the gradient is typically the arrow is in fact dropped. It's often written just like this. So the symbol is called nabla. It's an upside down triangle. So the gradient of f is the vector defined by the first component, or the I component of this vector is going to be partial f partial x, so the x partial derivative, and the y component of the gradient is going to be the partial f partial y. So another way of writing this vector is you have the x partial derivative in the first component and you have the y partial derivative in the second component. And what I'd like to point out to you is that this gradient vector is a vector in the domain of f. So just to give an example of how to parse this definition, suppose that my two-variable function f of xy looks like y times the natural log of x plus xy squared. And this example asks us to compute the gradient of this two-variable function at the point 1, 2. So 1, 2 is indeed a point in the domain of f. So that's good, meaning it makes perfect sense to plug in 1 for x and 2 for y in this expression. So if we take the partial derivative of this two-variable function with respect to x, what we find is this first term, so since we're taking the x partial derivative, we treat y as a constant. So the derivative of natural log of x is 1 over x, so the first term is y over x, and then y squared. And the y partial derivative is log x plus 2xy. So that the gradient at this point, 1 comma 2, means that you look at the partial derivative in the first with respect to x in the first component and with respect to y in the second component, and you evaluate both of these expressions when x is 1 and y is 2. So this becomes 2 over 1, that's what this is, plus 2 squared, that's what this is. And the second component of the vector is natural log of 1 is 0, and 2 times 1 times 2 is 4. So the vector that we get is 6, 4. 6 times I plus 4 times j. Okay, so that's an example of computing the gradient at a point. And the reason why we introduced this operation of taking the gradient of a scalar valued function is to address this question about how one might take the derivative of the scalar valued function in an arbitrary direction u. And the answer is this definition, which we call the directional derivative. So if f is a differentiable function of two variables, x and y, then we define the directional derivative of f in the direction u to be the dot product between this gradient vector and the vector u, which is the direction we want to take the derivative in. So here's how this works. Here's an example. You're asked to compute the directional derivative of the scalar valued function f of xy equals x squared sine 2y at the point 1 comma pi over 2. And we're going to take the derivative in the direction v, which is 3 times I minus 4 times j. So what should we do first? Well, the directional derivative is defined to be a dot product between the gradient of f and the given direction. So the first thing we should do is compute the gradient. So the gradient of f, which is this symbol here, the gradient, remember, is itself a vector, and the two components of the vector is partial x in the first component and partial y in the second component. So if I take the derivative of x squared sine 2y with respect to x, I get 2x sine 2y. And if I take the partial derivative with respect to y, I get 2x squared cosine 2y. And I plug, so I'm looking to find the directional derivative at this point. So if I plug in 1 for x and pi over 2 for y, I find in the end that I get this vector 0 comma minus 2. Okay, so all that we've done here is we've computed the gradient of our scalar valued function at the point 1 comma pi over 2. What we'd like to do is take the dot product between the gradient and the given vector v. However, v is not a unit vector, and yet in the definition of the directional derivative, u was required to be a unit vector. So what we need to do is rescale v such that it is a unit vector. So that's what this warning is about. If I rescale v so that it's a unit vector, and the way to do that is you take the vector v and you divide by the length of v. So the length of v is the square root of its first component squared plus its second component squared. So if we divide by the length, that's 1 over the square root of 9 plus 16. And then here's the original vector v. And so here's a vector 1/5 times the vector 3 comma minus 4. So this is a unit vector, and this is the unit vector 1/5 vector v. Okay, So v itself has length 5, so if we divide by 5, or we should really scalar multiply by 1/5, then the resulting vector will have unit length. 1/5 times v has unit length. And now finally we're left to compute this directional derivative, which is a dot product. So here is the gradient of f at this point, 1 comma pi over 2. Here is our unit vector u, which is 1/5 v. And we take this dot product and we see we get 8 over 5. Okay. The gradient will play a major role throughout the rest of this class. And here's the first instance of why the gradient of a scalar valued function is so important. And it's a big theorem. So this theorem is super duper important. So that's why I gave it this red star here. Super important theorem. It says, let's suppose that f is a differentiable function of two variables, f of x, y, is differentiable at this point, a comma b, in the domain of f. Then the first part of the theorem says that if the gradient of f is the zero vector, then the directional derivative of f in any direction, u, is also always zero. That makes perfect sense because the directional derivative of f in the direction u is a dot product between the gradient and that vector u. So if the gradient is zero, then certainly the dot product is zero. The second part is less obvious. It says that the direction of the maximum increase of f is given by the gradient direction. So if you recall, the gradient vector is a vector in the domain of f. So what part 2 tells you is that if you're in the domain of f and your point moves a little bit in the direction of the gradient vector, then that direction is the direction in which the height of the function increases the fastest. Part 3 says the exact opposite of that. So if you move in the direction minus the gradient, then that's the direction of minimum increase. And the last condition, the last part of the theorem says that if your gradient vector is not the zero vector, then that gradient vector is always orthogonal to the level sets of f at your point a comma b. Okay, we'll get more into why that's important in the next video.